Hi everyone. So today we're going to be starting the new section on planes. Okay, so don't forget entirely about the stuff we did on lines. We're going to be including that as well. Okay, so before we get onto planes, we need to discuss what is called a normal vector. Okay. So let's go on to what is a normal vector. So imagine we have some kind of surface, let's say like a tabletop, something like this. Okay, and we're looking at the surface of this table. A normal vector is a vector that is perpendicular to the surface. So if we look at the top of the table, then a normal vector will be something like this. Okay, so you see that it's sticking straight up from the table and is perpendicular to the table surface. Okay, so a normal vector, we usually call it N for normal. So we got N with the little line on top. Normal vector is a vector that is perpendicular. Remember that other word, perpendicular or orthogonal, to the given surface. Okay, so in the case of the table, you've got your vector pointing up like that. Okay, if we had a different situation, let's say you got your wall like that, and you wanted to know what the normal is, it would be a vector pointing away like this. Okay, again, it is perpendicular to the surface. Okay, and if we look at another example, let's say we have a ball like this, then at every point on the surface, we can also draw a normal. So if we look at the North Pole over here, the normal would be like that. So at that point, it's perpendicular to the surface. If we go here, let's say at this point, then the normal will be going this way. And again, it's perpendicular to the surface. So the normal can be different as we go around the surface, but at each point where the normal is located, it must be perpendicular. Yeah. So for example, at this North Pole, if you draw yourself the tangent line, it's perpendicular to that. If you go to the second point here, again, you draw your tangent line, it's perpendicular to that. Okay, so we can say the normal vector at a point is perpendicular to the tangent line. Okay, so if you're working in 2 dimensions, then you've got a tangent line. If you're working in 3 dimensions, we call it a tangent plane. Okay, and this is what we're going to be discussing now. Okay, this idea of a plane and its normal. Okay, so again, if we look at this idea of the ball, let's just draw that a bit bigger there. We've got the ball. At some point here, we've got a point. We can draw what's called the tangent plane, like that. So it's like if you take a piece of paper and put it on the ball, it's going to be tangent at just one point. Okay, so it's just touching it at one point. And we've got this 2D surface going there. Okay, so the normal would be perpendicular to the surface, like we had here with it being perpendicular to the table, perpendicular to the wall, same sort of thing. So it's going to be sticking out, a bit difficult to draw, but like that, and it is perpendicular to this tangent plane. Okay, so this 2D surface here, we call that the plane. Okay, and the vector that is perpendicular to the plane, we call that the normal to the plane. Okay, so the nice thing is that this plane is fully described by the normal. So if I give you a normal vector, then you can draw the plane that is perpendicular to it. For example, if I have this point here in space and I draw this normal, then all of the points or all of the vectors that are perpendicular to this will then make up the plane. So if we have a vector going this way, sorry, a bit difficult to draw this. Let's say here and here, where it's perpendicular to these vectors, then these two vectors, let's say v1 and v2, they must then lie in the plane. So, okay, so if you just imagine that as the plane, you've got these vectors along the plane or in the surface of the plane, and the normal is always perpendicular. So the collection of all these vectors, they make up the tangent plane, or they're in the tangent plane like that. Okay, so this is a bit of an angled view. If you want to look at it side on, like this. Okay, so now we're looking at it like that way. So then you've got your normal that is perpendicular to the plane, like that. So that's the plane. Okay, and then you've got all the vectors that are along the plane like that. Okay, and all of the vectors are perpendicular to the normal. Okay, like we had with this v1 and v2. So v1 lies in the plane. And so is perpendicular to the normal. Same thing with v2. v2 lies in the plane. And so is, again, perpendicular to the normal. So, in fact, any vector in the plane will then be perpendicular to the normal. Okay, that's going to be the defining feature of the plane. So, if I give you a plane and I give you the plane's normal, then all of the vectors in the plane are perpendicular to that normal. Okay, like we have in this picture here on the side. Okay, so if you've got your plane, you've got your normal, all of the vectors in the plane are perpendicular to that normal. Okay, so we're going to use this fact to come up with an equation for the plane. Okay, so some equation that you can use to plot the surface of the plane. Okay, or it describes all the points in the plane, however you want to say it. Okay, so the way we're going to do that is by creating this normal vector using some points that are in the plane. Okay, so how do we do that? Let's start again. We've got this plane. Okay, and what we need to do is generate some vectors in the plane. And then we're going to use that to construct the normal. And once we have the normal, we can find the equation for the plane. Okay, so let's say we've got this point here. Let's call that P. That's in the plane. Let's say we've got Q, that's also in the plane. And we've got R, that's also in the plane. Okay, so we need 3 points to find the equation of a plane. Okay, so P, Q, and R are 3 points in the plane or on the plane. Okay, so we're going to use these points to generate 2 vectors that lie on the plane, like we had in this picture here with v1 and v2. Okay, so let's do that. So we've got these points. So we're going to do a similar thing to what we did with the parallelogram and triangle stuff that we did before. We're going to construct two vectors. We can pick any point to be the starting point. Let's pick P. We're going to make a vector from P to Q, like that. And we're going to make a vector from P to R, like that. Let's call the first one V1, and we call the second one V2. Okay, so what did we do? V1, we found by taking the vector that's going to Q minus the vector that goes to P. Okay, remember we did that with the parallelogram stuff. So it will be the vector going to point Q minus the vector going to point P. Okay, that gives us V1. V2 is going to be from P to R. So it's going to be the vector going to R minus the vector going to P, and that gives us the vector that goes between the points. Okay, and V1 and V2 both have their base point or the starting point at P. So let's just highlight that. They both start here. V1 goes out to Q, V2 goes out to R. Okay, and both of them lie in the plane because we made them using points in the plane. So both V1 and V2 lie in the plane. Because we made them using points in the plane. Okay, so if we used points that were outside the plane, then the vectors would also go out the plane. But since all the points are in the plane or on the plane, then the vectors are also on the plane as well. Okay, so what we want to do now is find what the normal is. So remember what the normal was. That was the vector that is perpendicular to the plane. Okay, so we've got V1 and V2, and we want to find a vector that is perpendicular to both of them. So you should remember back when we did the cross product, if I have a vector A and a vector B, then the cross product is perpendicular to both of them. So remember, if we have A and B, then the cross product, A cross B, is perpendicular to A, and A cross B is perpendicular to B. The cross product is always perpendicular to both of them. So we can draw that in a little picture. If we've got A going this way, B going this way, then the cross product, let's do it the other way around. So the cross product goes in the right direction. So if we have A, B, then the cross product of A and B will go this way. Okay, and it's perpendicular to both of them. So A cross B. Remember, if we did B cross A, then the vector would go the other way. Okay, but I just wanted to go up just for the picture. Okay, so we know that this A cross B is perpendicular to both of them. So A and B, they lie in some plane, and A cross B is perpendicular to them. Okay, well, that's exactly what we want, because we've got here V1 and V2 lying in the plane, and we want something that is perpendicular to both of them. So we can just take the cross product. So if I do V2 cross V1, then we get a vector like this. Maybe if I draw it like, sorry, something like this maybe. Okay, there we go. So this is going to be V2 cross V1. and we call that the normal vector n. Okay, because it's perpendicular to the plane, that's exactly what we want the normal vector to do. Okay, so this is v2 cross v1, gives us the normal vector pointing that way. If we did v1 cross v2, we would also get a normal vector, but it would go the other way. So let's put that in gray. Say it goes this way. That would be v1 cross v2. Okay, so it's going the other way, but that's fine. It's still perpendicular. That's the important part. So it doesn't matter if the normal is pointing up or if it's pointing down. We only care that it's perpendicular to the plane. Okay, so later on, we will talk about orientations of the plane, and that's when it's important if it's up or down. For example, if you have like a page with writing on it, like imagine that's the page with writing, then you can either have the writing pointing up and then you pick that normal, or maybe you want the writing pointing down and then you pick the other normal. Okay, that's called an orientation. But for now, we're not interested in that. We're just picking any of the normals, either pointing up or pointing down. It doesn't matter for now. Okay, so you can do v2 cross v1 and get the upwards normal, or you could do v1 cross v2 and get the downwards normal. Both are fine. Okay, so we define the normal n as v1 cross v2. And of course, you could do it the other way around, and then you just get that minus sign, or you could do v2 cross v1. Okay, so it doesn't matter which way you do it. Okay, so this gives us the normal to the plane. Okay, so what we want to do now is use this normal to determine the equation for the plane. In other words, if I give you a point x, y, z, I'm going to ask, is this point in the plane or is it not in the plane? We want to check that. Okay, so let's go back to our picture here. P, Q, R. Let's say we have some new point S. Okay, we've got a point S, and the question is S in the plane or is it not in the plane? So the way we do that is we draw a vector from any of these points. It doesn't matter, because P, Q, and R, we know they're definitely in the plane. So you can pick any of them. We're going to draw a vector from them to S. So let's pick P because we used that one already. Okay, so it's going to be from P. Sorry, let's use green, from P to S. Okay, let's call that vector W. Okay, so we've got this vector and we want to know, is this vector in the plane? If it is in the plane, then we know that S is a point on the plane. If the vector is not in the plane, then S is not in the plane. Okay, so you see it's the same kind of question. Okay, so let S, X, Y, Z be some point in the plane. So we want it to be in the plane, and then we can use that to find the equation for the plane. And I'm going to leave it as X, Y, Z so that it can work for any point. It's not a specific point. Okay, so we've got W is equal to S, the vector going to S minus the vector going to P. So it's going to be S minus P. And just to make things easier, let's say P is given by X naught, Y naught, Z naught. Okay, so that's just in the plane. It's just some point in the plane. Okay, so this is going to be S, which is X, y, z, that's any point in the plane, minus p, we said that was x naught, y naught, z naught. That was, we know that's in the plane. That's already given to us, x naught, y naught, z naught. Okay, we can combine this to get a single vector, x minus x naught, y minus y naught, and z minus z naught. Okay, so that is our vector w. Now, we know that w is in the plane because s is in the plane, p is in the plane, and we know that n is always perpendicular to the plane. So, since w is in the plane, and n is perpendicular to all vectors in the plane, we have w dot product with n must be 0. Okay, so if you want to know why it's equal to 0, let's look at the cosine form of this. So remember that w dot n, we can either write this using the components. Remember, like a dot b is a1 b1 plus a2 b2 and so on. Or we could write this as the length of w times the length of n cos the angle between them. Now, if they're perpendicular, then the angle must be 90. Perpendicular means the angle is 90, and so cosine of 90 is 0, which means this whole thing goes to 0. And that explains why this dot product is 0. Okay. Now, let's fill in the values and see if we can find the full equation of the plane. So w, remember what that was? That was x minus x naught, y minus y naught, z minus z naught. Okay, dot product with the normal, let's just say that is a, b, c. And that's 0. Okay, so remember the normal, you have to do that cross product of v1 and v2. That gives you the normal. That's going to give you some 3 components. I'm just calling them a, b, c. Okay, so let's just make a little note here. The normal I'm saying is a, b, c. Okay, we don't know exactly what they are because we don't have the other points in the plane, but we can just call it a, b, c for now. Okay, so let's do the dot product. That means we multiply the first components and then add it to the product of the second components and then add it to the product of the third components. So we're going to get a times x minus x naught plus b times y minus y naught plus c times z minus z naught is equal to 0. Okay, so this gives us the equation for the plane. So I'm just going to put this in red. Okay, so that's the equation of the plane. So if we know a point in the plane, x naught, y naught, z naught, and we know the normal, then we can determine if another point is in the plane or not. Okay, so remember, the normal is a, b, c, and some point in the plane P is given by x naught, y naught, z naught. So if we know those 2 bits of information, then we can determine if x, y, z is in the plane or not. So we just substitute the points in. If we get 0, then we know that the point is in the plane. If we get some other value, then we know it's not in the plane. Okay, so we can use this formula as is, but there's a nice way of simplifying this into a nice single equation that we can use. So let's write this ax minus x naught plus by minus y naught plus c z minus z naught is equal to 0. Okay, so you might not see it like this all the time, but if we expand this out, we get the standard form that you'll see quite often. So if we expand this out, we get a times x minus a times x naught plus b times y minus b times y naught plus c times z minus c times z naught is equal to 0. Okay, so now minus a times x naught, that's a constant because the normal is a constant, the points are constant, so a times x naught, that's a constant. B times y naught, that's also a constant. C times z naught, that's also a constant. So let's take all these constants and put it to the other side. So we're going to get ax plus by plus cz is equal to ax naught plus by naught plus cz naught. Okay, and like I said, all of the stuff on the right-hand side, this is all a constant. Okay, because we've got a constant plus a constant plus a constant, that just gives us another constant. So let's call this constant d. Okay, so this gives us ax plus by plus cz is equal to d. And this is the form that you might see more often. Okay, so this is the equation for a plane. Okay, so that's going to be the equation that we're going to be using. Okay, so we've got this equation. So what we want to do now is try and draw the plane. Now, the plane is infinite. So if we go back up here to the picture, so I only drew a little portion of the plane here, but technically this plane goes on forever. Okay, it's an infinite sheet of paper, if you want to think of it like that. So when we draw it, we can't draw everything. So we only draw a piece of the plane. So we only draw the little portion that fits inside one of the quadrants. Okay, so in 2D, we call it a quadrant. In 3D, we call it an octant. So if I just draw it here, something like this, X, Y, and Z. So we're used to drawing things in the XY plane, like all of your graphs and lines and so on. In 3D, we have to draw in this space, okay, because there's 3 dimensions. So we can't draw the full plane. So what we do instead is we find the intercepts of the plane. So the first thing is we find the intercept along the x-axis. And we know how to do that because if we're along the x-axis, we know that z and y are both 0. So z equals y equals 0. That gives us our x-intercept. We can also find the y-intercept. Okay, and we know what the y-intercept means. It means x is equal to z, which is equal to 0, like that. And we can also find the z-intercept. Maybe it's up here somewhere. We know what that means. We know x is equal to y is equal to 0. Okay, so we found all 3 intercepts. And to draw in the plane, we just connect them together. So there, there, and there. And that is the portion of the plane that we draw in. So we can color this in. So this little triangle, that is the portion of the plane in the first octant, okay, where X, Y, Z are all positive. Okay. So if you want to imagine like a bigger portion of this, it would be something like this. Okay, we've got X, Y, Z. So imagine just like a big portion like this cutting through. Okay, but again, that goes on forever, right? But we're only interested in this little portion with that intercept, this intercept here, and then the y-intercept that's over here. Okay, so again, you need to imagine it in 3D, but then we only draw this section, this triangle section here. Okay, so out of the full infinite page that I've drawn here, we only draw this bit here. Okay, but that's enough to show the general idea of where the plane is going. So it gives us like the angle of the plane and so on. Okay, yeah, so don't try to draw the full plane. You only need to find the intercepts and then connect them together. And then that will give you the portion of the plane that we're interested in. Okay, so let's give you a little homework. Sketch the plane given by 2x minus y plus 4z is equal to 2. Okay, so I've given you the A, B, C, and D. Okay, so you can use this to find the intercepts, connect the intercepts, and then you know what that piece of the plane looks like. Okay, so that's the general idea of sketching a plane. Next week, we're going to look at more examples of sketching different planes. Okay, so different orientations of the planes. And then we will also look at finding the equation of a plane. Okay, so like here, we wrote it with the A, B, and C. We'll look at examples on how we found the normal to find those values of A, B, and C. Okay, but for now, this little example should help you with the mental picture of what these planes look like. Okay, any questions about what we've done today? Okay, I did post on the WhatsApp group, but I'll just say it again. I have posted an assignment, okay, on the Learn 2022. It's under the assignment section. So it's a compulsory assignment, and the reason I put it there is to help boost your test 1 marks. Okay, so quite a few students got less than 50. So I'm going to use your test mark together with the assignment to hopefully get a better mark for you. Okay. Okay, and it is compulsory for everyone. Okay, so everyone has to do it. And then I'll use that mark together with your test 1 mark. Okay, any questions on that? Okay, cool. I'll see all of you on Monday then. Yeah, bye everyone.